We now shift to Chapter 6, Correlation. Our goal is to understand how two variables move together, their direction and strength of association. Before we jump into causal claims, we will build from pictures to numbers, then to formal tests, and finally discuss what correlation can and cannot tell us. By the end of this chapter, we should be able to make and read scatter plot, explain covariate and how it moves correlation, and compute and interpret Pearson's R and discuss causality limit, and use non-parametric measures, Spearman's law and Kendall tau. Variance is here. It is the average squared deviation from the mean, like this. This is the mean of the sample. This is the mean of sample x bar, and individual value is xi. And squared divided by sample size n minus 1. This is important because covariance is the two variables analog. Instead of scaling only x, one variable's deviation, we multiply the deviation of x and y in covariance case. Understanding variance first makes the leap to covariance and then to correlation much easier. This is the covariance. This is the formula of covariance. If we want to know whether the one variable increases and the other tend to increase or not, we use covariance. We can compute the covariance. If the one variable increases when the other increases, the covariance is positive. If one rises and others falls, it is negative. And if they vary independently, the covariance is near zero. Mathematically, we can take each observation's deviation from its means and multiply them. Take deviations and multiply them and sum of them. If the product is mostly positive, the variable will move in the same direction. If mostly negative, they move oppositely. Covariance captures direction, but not the strength in a standard way. We will fix that in the correlation a few after the slide. I want to continue the covariance explanation. This is the covariance and this is the variance. The different point is here. There is a different and covariance case, x deviation multiply y deviation. Variance case, x deviation multiply x deviations. They look almost identical except that the variance multiplies the deviation by itself, while covariance multiplies x deviation by y's deviation. So variance is a special case. This is a special case of covariance, where both variables are the same. This is a graphical explanation. Let's practice with the small numbers. Suppose that we have 5 pairs, 1, 2, 3, 4, 5 pairs, x and y values. We compute each deviation from the mean and multiply them, then average those product. X is here and y is here. X is blue line, y is black line. Deviation of x is minus 0.4, minus 1.4, minus 1.4, plus 0.6. Y deviation is minus 3, minus 2, minus 1, plus 2. and multiply them, each of them, minus 0.4 multiply minus 3, the gray area, and purple area minus 1.4 multiply minus 2, and sky blue area, green area, blue area. And finally, we sum all the deviations multiplied deviations equals here and divided by n minus 1, sample size minus 1. Then we can get the covariance. If products are mixed, the covariance will be small, meaning a weak linear relationship. This hands-on computation shows that the covariance is literally the average of joint deviations from means. This is the variance. Variance only think about the y itself and x itself. This is different from covariance and variance. Covariance has big limitations. It depends on the unit of measurement. If x and y are measured in miles case, converting the same data to kilometers, multiply each values by 1.6. So covariance is multiplied 1.6. So the value is 11. 1.6 multiplied 1.6 is 2.56. So the 2.56 multiplied 2.56 multiplied 4.25 is almost 11. So the value is different in the unit. That means you cannot directly compare the covariances across different scales. To solve them, we need to standardize. We standardize by dividing covariance by the standard deviations of x and y. And that gives the correlation coefficient. That is a correlation. Correlation is divided by standard deviations x and y. This is a correlation. And this range is from -1 to +1. So we can compare the strength of the relationship. This is the figure. This is the general correlation coefficient. That is Pearson's correlation coefficient. This is the graph. R equal -1 case is here. R equal +1 case is here. R equal 0.6 case is here. The right side is upper. In this case, minus case, right side is lower. And if R equals 0, the point is scattered. And shape is like circle or not direction. Pearson's R is the most common measure. It standardizes the co-movement of x and y, and so we can compare across variables with different units. So the correlation is very famous. Think of R as a unit-free linear association index that we will compute from the covariance. This is the just a rule of thumb, but the very informative rule. R ranges from -1 to +1, and 0 means no relationship. The rule of thumb effect size is here. Plus minus 0.1 is small effect. Plus minus 0.3 is medium. Plus minus 0.5 is large effect. Please remember the linear is the key word. So non-linear relationship, it is difficult to assess the relationship using the Pearson's correlation coefficient. The Pearson's correlation coefficient pros and cons is here. First, precisely measure linear strengths and directions. And second, the widely used and understood. And standardized -1, 2, +1, so easy to compare. And basis for many other statistical techniques. For example, regression or principal component analysis, and efficient with normally distributed data. If the data is normally distributed, this is efficient. Cons is here. Only measures linear relationship. Misses if the relationship is curved. And sensitive to outliers. And assume normality. This is a big assumptions. And not suitable for ordinary dataset. Can be misleading if assumptions are violated. It's related to the number 3. Correlation formula is here again. This removes the unit and bonds the result between -1 to +1. We can calculate the correlation like here. Firstly, we calculate the covariance in the same way as mentioned before. Minus 0.4 multiplied -3 minus plus the -1.4 multiplied -2. Multiply these x and y and sum of them, that is, and divided by sample size -1, that is covariance, and divided by the standard deviation. In this case, 1.67 and 2.92. Then we get the 0.87. This is the correlation. So this is the strong positive correlation. Correlation is here. Test for correlation is this. When we test whether the correlation is different from 0, we want to statistic with an approximately normal sampling distribution. Two standard route is here. First is R's correlation test. That gives you R a test, statistics, p-value, and a confidence interval. And also we have the Fisher's D method. That's the this is the basic method to make the sampling distribution approximately normal here. And we check. We can conduct significant test and estimate confidence interval using the Z-score. The corresponding table is listed at the end of the textbook. A Z-value tells you how many standard errors your estimate is from the null value. Large D, then the small p, and small z would be the large P. In practice, you do not need to memorize the full table. In R, the correlation test reports the p-value directly, and you can check the textbook. Okay, let's calculate the correlation using R. Our example is 103 student. Variable is time spent revising and exam performance, exam anxiety, and gender. We will explore the signs and size of the correlations. There is some correlation test command, call and call.test and rcall. Today, rcall in HMISC package is preferred to use by many researchers and brand researchers because in these regions HMSC HMISC is the not only Pearson's correlation coefficient, Spearman's rank correlation coefficient and Kendall coefficient can be calculated, so very flexible, and p-value can also be calculated, and handling the dataset would be good. So rcall is very useful today. But in this chapter, we also check the call and maybe call test. Okay, firstly, install the packages. This is a chapter 6 command. Firstly, set the directory and install packages. Okay, then initiate packages. Library HMISC, library ggplot2, library polycall. And next is the command Pearson's correlations, the most standard method. Is a dataset, exam anxiety dataset. This is the explanation, right? Use only complete observations with no missing value in all variables. However, this does not work because the data contains text. And this command checks whether there is a column named gender in the column named obtained. And extension mark negates the above result. In other words, it selects all columns except gender. This is a robust way to avoid errors when a data frame mixed text and numbers. I want to avoid the mixture of the text and numbers. Gender contains text, so I would like to avoid the gender variables like this. So after that, we conduct call. Then we can calculate the correlation, Pearson's correlations, exam, anxiety, device. Both forms produce the same 3 multiply 3 matrix for the chosen variables. This is the explanation. This is picking up only exam and anxiety. Pearson's correlation is default, so we do not need to specify them. This one and this one yield same result. Okay, I would like to check the result. Some data set install and exam data overhead. Exam data. I think we can check the result. We successfully install the data. It's okay. Head shows the six rows of the data. So we can check the exam data is already used. We can use the exam data or not. And after that, we carry out call command. Then we get correlation, the basic correlations. Px with gender and method is Pearson. Pearson's method. And this is the we check exam. Also the exam data too. We specify exam anxiety device and for exam data too. Is the save yes. And each relationship exam and exam, anxiety and anxiety, device and device. Same variable is the correlation is 1 because it's totally same. And we can check exam and anxiety's relationship. This is negative minus 0.44. So it is negatively related. And revise and take exam is positive plus 0.39. So it's the positively related. It has positive correlations. So exam result for the exam result, anxiety is bad, but revision is better. That is the relationship. Okay, next, another way to get core. Next, we use the HMISC R core RCORR exam matrix. This is the more convenient, I think. HIMC. This command calls the rcore function in the HMISC packages. So we can use this command. We call the R function, and at the same time, we use the RHMISC package we designate. This is the dataset. What is the variables? Okay, let's check the result another way. Exam matrix is here. Add exam matrix. And this is the exam matrix dataset, but the sample size is too large. Then it is difficult to see all the dataset. So it is more safe to add head before the dataset name. Then this is limited to 6 rows. And we check the HIMSC command. Like this. This is the correlation. And this is the p value. P value is here, and this is the correlation. when you show the output, this is the correlation matrix, and this is the p-value matrix, which check the pairs are statistically significant or not. So this is a statistically significant, and the correlation is here. I think it's almost the same. Sometimes the very slight differences between the different calculation packages, but almost same. 0 minus 0.44, 0.40 is the relationship, and these are statistically significant because p-value shows the 0. This is the result, and also the another way, the call test command also shows the Pearson's correlation. Can show the result. Before that, call test command, sorry, the R code, I skipped the call test command because the result is almost same. Correlation is the minus 0.7. Using call test, then I can check the Pearson's correlations one by one, and p-value is very close to 0. It is the same as before. It is same as here. The relationship is minus 0.71, and this is significant. Minus 0.702, 709, and p-value is significant. It is same. And next, we want to calculate the R squared. Definition: squaring the Pearson's correlations R gives R squared, the proportion of variance in one variable that is linearly associated with the others. Range is 0 to 1 because it's squared, and the range of the Pearson's correlation is minus 1 to 1. So R squared's range is 0 to 1. Direction is lost because of R and minus R gives the same R squared. In R, you can square the correlation matrix and multiply by 100 to get percentage variance explained like this. Calculate correlation and squared and multiply 100. So how much association there is, you can calculate. This is the result here. This is the R square. Exam is 100% explained by exam. This is the of course the exam is explained by exam. And anxiety is about 20%. Revise is about 6%. And anxiety and revise relationship is about 50% explained. Okay, next is the one point of the correlation and causality. The correlation is not the causality. So I think you know this meaning, but I want to say this again. For example, there is the classic point. This is the third variable problem and direction of causality. A hidden variables. Third variable problem is that a hidden variable can drive both x and y and creating a spurious correlations. And the direction of causality is even strong R squared. You cannot tell whether x to y or the directions x to y or y to x or both. So use correlation to describe core movement and use research design and identification to the causal effect. The reverse causality can make interpretation misleading. So please check the relationship. If you want to show the causality, then you need to apply another method. Showing Spearman's method, sorry, showing only the correlation is not adequate. Applying another method like the instrumental variable or random control trials or such kind of method is required. Okay, next is Spearman's law. This is a non-parametric measure. When assumptions for Pearson's correlation is weak, for example, the strong outliers, strong skews, and ordinal scales, then we cannot Pearson's R. We cannot calculate. We can calculate, but the Pearson's R is not match the data. So then we need to apply the other method, non-parametric method. But non-parametric method is Spearman's law. It replaces low values with rank and measure monotonic associations. If one variable tends to go up as the other goes up, low will be high. It use rankings. Ranking is the matter and the magnitude is not the matter. Key features robust to outliers because the one outlier's magnitude is very high, then we can ignore the magnitude. Work with ordinal dataset and detect monotonic, but nonlinear patterns that Pearson can miss. We will compute it shortly with the method called Spearman in call or call test in R. Interpretation is monotonic. Like this. In this case, Spearman's correlation equals 1, but Pearson's correlation equals 0.88 because it's not linear. But the order is the same, so the Spearman's correlation equals 1. This is the pros and cons for Spearman's law indicator. This is robust to outliers and can detect non-linear but non-monotonic relationship and works for ordinal data. Ordinal dataset, we cannot use the Pearson's correlation, but we can use the Spearman's law. And does not require normally distributed dataset and fewer strict distributional assumptions than Pearson. Cons is here less powerful than Pearson when the data are truly normal and linear. If the dataset is very desirable, then we can and it is efficient to apply the Pearson's R. To convert values to ranks, losing some information. We cannot assess the difference of mean. We cannot assess the average. Not ideal for pure interval or ratio inference about linear effects. Ties need care. if there is a lot of Thai dataset, Thai ranks, then we need to handle the dataset, because if there is a lot of same rank, this Spearman's law do not work well. Okay, next is the calculation of Spearman's law using our layer data. The biggest layer dataset we use here. We install the dataset and method is Spearman. In the slide here, method is Spearman. And in this case, alternative equal less, conduct one-sided test of negative correlation. We can conduct this command, and then this is the result. Oh, I see. Cannot compute exact p-value with ties. If there is a ties values, there is the warnings here. But this command call and call test also yields same result, minus 0.37. Spearman's rank correlation law. Estimated value is here and p-value is here, and warning message. There is a tie value, so please check the dataset. If there is a lot of tie value, so the result would be not informative. This is the result. Okay, next command is the Kendall rank correlation coefficient, Kendall tau. Kendall tau measures the ordinal association by counting concordant and discordant pairs. High tau means the ordering of observations is similar across the two variables. When ties are present, please use Kendall's tau minus b. Kendall tau minus b. Tau is more intuitive with small samples and heavy tie ranks. It is robust to outliers and, like Spearman, target monotonic association rather than linearity. There are many samples with the same rank. It means that the correlation is high. Idea is here. Tau is high when the relative ordering of observations. And this is the pros and cons for Kendall tau. Pros are the robust to outliers, detect monotonic association, and works well for ordinal dataset, often more intuitive with small samples. It's strong for small samples. And interpret argument with concordant versus discordant. But there is some cons. More computationally intensive than Spearman, and typically less powerful than Pearson under normal linear relationship, and not as widely used as Spearman or Pearson. And ties can affect estimate. So in that case, please use the tau minus b, Kendall's tau minus b. Sorry. and may underestimate the strength of association in some cases. Okay, now go ahead. Kendall tau, let's calculate. Then the call and method equals Kendall, or call test method equals Kendall. Then we can calculate the Kendall tau in the R command. Kendall tau. This one. Can calculate. Oh, this is the Kendall tau. Like this. This is the Kendall tau statistics. So if the sample is randomly drawn and the random sample and the sample size is enough large, we can calculate the normal correlations, Pearson's correlations. But that the distribution is not normal, then the Spearman's correlation can be used. Also, the Kendall tau can be used. And Kendall tau is good for the small sample. And also, if Kendall tau minus b is used, then that is the strong for also the ties are present case. It is useful. So please use the best way, the suitable way for your statistical analysis. Only check the Pearson's correlation is the very risky choice, I think. So we skip the bootstrap. If the sample size is very small, we can conduct the bootstrap method. And I show the bootstrap method in the slide and in the code. Then you can apply if you are interested in. That's that. In today's lecture, I'll skip this part. And this is the procedure. Firstly, normality test, Shapiro-Wilk test, and Leven's test. Shapiro-Wilk test the skewness, and Leven's test the equal variance. And significant, in that case, insignificant, and the sample size is not so much, then please use the non-parametric test. For example, sample size is under 60 or under 120. Non-parametric test would be preferable. For example, Kendall tau test, small sample. Some textbook says the sample size is under 20 or 30. Kendall tau can be considered. And if the sample size is enough large, or the parametric test, the normality assumptions is satisfied, then you can use the t-test in the small sample and z-test in the large sample. Okay, this is the lecture 6, and the homework is here. Details homework is provided via util, so please check the util. Please use the same data as before homework, the AER library, and you can get the star dataset. Okay, thank you very much for listening.